In Chapter 12, we continue the discussion of hypothesis testing, now focusing on linear regression and correlation. In short, we are going to look and see if there is a relationship that is linear between two variables. We are going to have paired data, so we will be able to create scattered plots. When we collect data and we suspect there might be a relationship, we want to do scatter plots. Each data point would have an x value and a y value, and we can plot these points to see if there's a relationship or if there appears to be a relationship at least. As we look at these scatter plots, we will be looking for patterns. We would want to see if there's a strong linear pattern, maybe a linear pattern with one deviation, a negative linear pattern that's strong, or maybe there's a negative linear pattern that's a little bit weaker. Or it could be that we see that there's no pattern at all. As a statistician, we want to find the equation for the line that best represents the data values. Lines will be of the form y equals a plus bx, where a is the y-intercept and b is the slope of the line. We use this form because our calculator uses this form as well, and it's nice to be able to depend on our calculator every now and then at least. There is a function on our calculator that we can use to compute the values a and b. If you go to Stat, then over to Calc, you'll find the function linreg a plus bx. While this function is nice, in practice we end up not using it because there's another function that ends up giving us more. But for now, we have this function. When would we want to find regression lines? Well, we only want to find regression lines when our data appears to have a linear relationship. A linear relationship meaning it's a straight line. Now we were able to visualize this a little bit with our scatter plots. If there appears to be a relationship, we can find the regression line. Though this is not a very strong way to determine when we want to find regression lines. And it also does not tell us how good this regression line actually is. We need something a little bit more sophisticated. We need something that measures the strength of the relationship between the variables. And we do have a statistical tool for that, and it's called the correlation between the two variables, the correlation coefficient. It's also called the coefficient of correlation. And it's abbreviated as R, and R equals this formula. Now this looks like quite a bit of work. It's not super easy to do by hand. The good news is your calculator will compute this when you perform your hypothesis test, the linreg-t test. A little bit more about your correlation coefficient. The correlation coefficient tells you how strong the linear relationship between x and y is. Now notice that it's for linear relationships. The value of our correlation coefficient is always between -1 and 1. When r equals 0, there is no relationship. R equals -1 is a perfect negative relationship, and R equals 1 is a perfect positive relationship. The closer the absolute value of R is to 1, the stronger the relationship. Let's look at this example and let's try to determine which goes with which. All of the options listed to the right are values for R, the correlation coefficient. Each one goes with a graph here. As we look at the top left graph, it appears to have a positive relationship. It looks like it might be a little bit strong. Let's keep looking through them though and kind of discuss what we think we see, and then we'll come back and match them up. Looking at the top left one, we see that it looks like there might be a positive relationship, but it's not very strong looking at all. It definitely looks like it's weaker than the first one we looked at. Then we look at the bottom left one. We see that it kind of looks like there's a negative relationship going on there, but it doesn't look very strong because there's quite a few outliers. And then looking at the bottom right one, we see that there's a negative relationship. Not super strong, but stronger than the previous one that we looked at. So now looking at our options for a correlation coefficient of negative 0.77, correlation coefficient of negative 0.19. Those are the two negative ones. We said the negative relationships were those that we saw on the bottom. The stronger one was the bottom right. The weaker of the two negative relationships was the bottom left. Then our positive relationships, we see a correlation coefficient of 0.74 and a correlation coefficient of 0.21. The stronger of the two positive relationships appeared to be the top left. The weaker of the two positive relationships appeared to be the top right. So how good are the predictions from the regression line that we compute? Well, the regression line can only be used to predict values of y based on values of x. The stronger the relationship between x and y, the better the predictions. A nice mathematical way of stating how good the predictions are is r squared, which is the coefficient of determination. The coefficient of determination is found by just squaring the correlation coefficient. Instead of representing this as a decimal, though, it's often represented as a percent. Now, hypothesis testing. From gathering data and computing the line of regression and correlation coefficient, we still cannot statistically state that there is a relationship between the two variables. If we think a correlation coefficient is strong enough, then we could test to see if there is a statistical relationship. We are performing a test on R, the correlation coefficient of our sample, to see if we think the population correlation coefficient rho is equal to 0 or not, thus stating that there is no relationship or that there is a relationship. When performing hypothesis tests for linear regression, our hypotheses will always be the null hypothesis that rho equals 0, meaning there's not a relationship, or that rho equals 0, meaning there is a relationship. The degrees of freedom will always be n minus 2, and our test value, t, is equal to r times the square root of n minus 2 divided by the square root of 1 minus r squared. Now, we said r wasn't easy to find by hand, so because of that, we will rely on our calculator for performing these tests. Now, there's 5 steps for every time we do a hypothesis test, and you should be getting familiar with these 5 steps by this point. Step 1, state your hypotheses and identify the claim. Step 2, state your level of significance and your critical value if you're doing the traditional method. Find your test value and your p-value if you're doing the p-value method, which I believe most of you are at this point. Then you make your decision and write a sentence. So let's look at an example together. A student wants to see if the number of times a book has been checked out of the library in the past year and the number of pages in the book are related. She guesses that the number of times a book has been checked out of the library in the past year will be a predictor of the number of pages. She randomly sampled 10 books from the library. Test her claim at a 0.01 level of significance. Now, by looking at this data, we could go ahead and draw a scatter plot just to kind of visualize what's going on. I've done that for you here by using Excel. From looking at this, it looks like there might be a line that's pretty much straight across horizontal, but we wouldn't be able to get a very good line. So let's go ahead and perform a hypothesis test. Now, whether we find a strong correlation coefficient or not, we're going to go ahead and perform the test just for the practice. Now, so even though it does not appear to have too strong a correlation, we're going to go ahead and compute the correlation coefficient and the regression line and test to see if there's a relationship. So again, there's our data. Using the Lin-Reg t-test on your calculator, we would find that R equals negative 0.0936. Now again, we found this R by using the Lin-Reg t-test, and this is found by going to Stat on your calculator, over to Tests, and then scrolling down. It is towards the bottom of the list. You will want your data values entered into list 1 and list 2 before you select the test. So you found R to be negative 0.0936, which is a fairly weak correlation coefficient, but we've already found all the values, or at least our calculator has them sitting in front of us. So let's go ahead and list our regression line. Our regression line should be y equals 324.513 minus 0.3523 times x. So our hypothesis test, even though we're pretty certain it looks like there's no relationship, we'll test it anyway. Our hypothesis test, null hypothesis, rho equals 0, meaning there's no relationship, and the alternative hypothesis, rho does not equal 0, meaning there is a relationship. That's the claim that the student was making. Alpha equals 0.01, we're using the student t-distribution, hence the Lin-Reg t-test, and we have negative 3.355 for our left critical value, and 3.355 for our right critical value. Our test value ends up being negative 0.266, and our p-value is 0.797. So our p-value is greater than alpha, which tells us do not reject the null hypothesis. We also could see that our t-value is not in the tail areas if we were to draw a picture. So we're able to say that there is not enough evidence to support the claim that there is a relationship between the number of times a book is checked out and the number of pages in the book. A student wants to see if the weight of a paperback book and the number of pages in the book are related. She guesses that the weight of the book will be a predictor of the number of pages it has. She randomly selects 11 books from the library, tests her claim at a 0.05 level of significance. We would enter each list into a list in our calculator. So list 1 is weight in ounces, list 2 is number of pages. We would find that R equals 0.567 when we perform the Lin-Reg t-test. This makes it look like there might be a relationship, so let's go ahead and list our regression line. Our regression line is 46.384 plus 1.362 times x. Our null hypothesis is rho equals 0, which means there is no relationship, and our alternative hypothesis is rho does not equal 0, which means there is a relationship, and that is our claim. So alpha equals 0.05. Our test value comes out to be 2.065, and our p-value is 0.069. Thus, we decide do not reject the null hypothesis, and there is not enough evidence to support the claim that there is a relationship between the number of times the book is checked out and the number of pages in the book.